boundary conditions between the boundary of conductors and insulators or free space, we need to know certain properties of conductors. So the properties like the resistance under the influence of uniform field, non-uniform field, that we are going to discuss here and derive the necessary equations. So let us proceed. The valence electrons in the outermost orbit of the conductors are responsible for conductivity. When some electric field is applied, some force is exerted on these electrons, and that force F, it is given as F equal to E into E, where minus E, it is the charge on the electron, and E, it is the applied electric field. Now because of this force, the electrons start moving inside the conductors and they collide with the lattice structure within the conductor, and because of this the electron velocity is limited and it attains a constant average velocity. Now this velocity is called as the drift velocity. Now more the applied electric field, more is the velocity. So I can say the drift velocity is directly proportional to the applied electric field E. And this proportionality constant, it is called the mobility of the electrons. Now we can write current density as J equal to rho E into Vd, where rho E, it is the electron charge density, and Vd, it is the velocity with which the charge is moving within the conductor. So just now we have defined it, called as the drift velocity. The drift velocity, what we have written from this equation, this we substitute here. So we can write J as minus rho E mu E into E. Now this term minus rho E mu E we represent as sigma. So we write this conductivity in terms of sigma and E, where this sigma, it is called as the conductivity of the metal, and this we define as the point form of Ohm's law. Now let us assume a conductor of length L across which some voltage V is applied. So we can say that the electric field inside the conductor is now applied voltage divided by the length of the conductor, that is V by L. So this is the electric field here in volts per meter, and this electric field is uniform throughout this conductor. So E is equal to V by L, and this electric field is uniform throughout the conductor. The cross section area of this conductor is S. Now previously we have seen the current flowing through the conductor I is written in terms of the current density as J dot ds. So the actual current density flowing in this conductor is in this direction, that is normal to this surface ds. So this component along this direction is given as J dot ds. So if I integrate this over the entire surface of this conductor, that gives me this current flowing through the conductor I. Now if this J, it is in the normal direction of this ds, it is in the normal direction of this surface, then in that case integral J dot ds, that becomes simply product of this J and S. So assuming that the current density, it is normal to the surface, this integral J dot ds, it reduces to simply product of J into S, because current direction is normal to the surface. Now the current density is current divided by the surface, that is ampere per meter square. And in the previous slide we have defined the current density as sigma into E. Now writing this E, as V by L here, substituting this E as V by L, we can write J equal to sigma into V upon L. Now rearranging this equation, I can write V equal to L upon sigma S into I. Now from Ohm's law, we know V is equal to IR. So from this equation, I can say the resistance of the conductor R is nothing but L upon sigma S. So this is the resistance of the conductor under the influence of some uniform electric field intensity E here. So it depends upon the length of the conductor, the cross-sectional area of the conductor S, and the conductivity of the material. Now let us define the resistance of a conductor when the electric field intensity it is not uniform. So let us find out the formula for that. So under non-uniform fields, the current I is integral J dot ds. So just now we have discussed the actual current entering inside this surface area is nothing but J dot ds. If I assume some small differential surface area here and integrating this over the entire surface, that gives me the total current entering inside this conductor. Now the voltage across this conductor, let us say VAB, if this is the point A and this is the point B, voltage along this conductor is given as minus integral B to A E dot dl. So that is the line integral E dot dl. Now as E is not uniform, we cannot take this E outside of this integral, what we did earlier. So this is the expression for current and this flowing through the conductor, and this is the expression for voltage across the conductor VAB under the influence of non-uniform fields. So resistance is voltage divided by current. So we substitute this equation here for voltage and the equation for current here. So this gives me equation for resistance of the conductor when the applied electric field is non-uniform. So ratio of minus B to A E dot dl divided by surface integral sigma E dot ds. So J we substitute as sigma E here. So this is about the resistance of the conductor under the influence of uniform field and non-uniform field.